All right, I'm back again. This could be the final recorded lesson of the class. So hopefully everybody appreciates this. I took the last one, which was about my video about the derivative, and I compiled all the questions. This is from period 4. What is the use of the derivative? How do you graph a derivative? How do you graph a derivative? How can you accurately graph a derivative of a function? Can we go over how to do the trick with f of x plus h minus f of x over h? That's called the difference quotient, and yes, we can. Do you ever use the derivative formula with a graph? How do you best graph the derivative? What is the main function of a derivative, and why is it associated with f of x plus h over h? Can I get a definition of a derivative and get a more simple example of one? Will the slopes of the original derivative always be the same? How do you know what the most important points are when trying to graph the derivative? Is there an accurate way to graph the derivative? What are the important points to include? For derivatives, does it relate to piecewise functions when you split up the function? The answer is yes. When it comes to points where the slope is 0, does it even matter that it is at 0 because it's only 1 point? That's an important question where the slope is 0. One that bleeds into a larger section of calculus, like a whole chapter on extreme values. And I'll get to it in a little bit. Do all of the trig functions have a derivative? Yes, they do. Why do we actually, now this is period 5, why do we actually care about tangents? What do you use tangents for? What is tangents trig term derivative? Does the power rule make the old method obsolete? How do you take the derivative of an equation that has a tangent, cosine, or sine value in it? As far as making the old method obsolete, I think the process will be one that you won't have to do anymore, but the concept is an important one for you to understand. So I'm going to go over that in a second. I'm confused by what you meant by the derivative is equal to instantaneous rate of change. How does the difference quotient relate to the derivative? I understand how to find the derivative from a polynomial, but I'm not really understanding how it relates to IROC. Is the slope function the same as the first derivative? Could we review the definition of a derivative and what the first derivative in particular is? What are slope functions used for? What are their applications? These are all good questions. I can sense that you guys are anxious to get to the part where I actually answer some of these questions, but just hold on. I didn't really understand the last part of the video with the written functions when you take the derivative of the function. Explain power rules. Power rules you should need more help with because I just barely explained them, but those will stick. You'll get those. What are the rules for transferring powers within an equation? Is it legal to implement the term derivative now? It is. Yes, now it is. Why did we just learn this? How does this relate to other topics or apply to other topics? When will we use this? What does h represent? So when h is greater than 0, that's when the slope is 0. Why does derivative measure? Why are tangents important? What does derivative measure? Sorry. So a derivative graph is like if you made the y value slope of the original graph and the x value, or whatever the x value original graph was, right? Okay, so I think what I'm hearing is people. I heard several questions about tangents, and I think there's two different things. There's a tangent line, and then there's the tangent function. But let's see if I can see where I can get to by looking at the tangent function. Is one that we haven't looked at a lot. So let's look at the tangent function. Tangent is, what is it? Opposite over adjacent. It's the ratio of the y value to the x value, and the graph that it makes looks like this. Let's see. Probably this mode is going to be better. I'm really kind of not interested in this whole region here. So let's go maybe from negative pi to pi. And we'll only look at that part of the graph. Well, it's probably going to make sense if we do the same thing in our viewing window. So this will go from negative pi to pi. And let's say I want to know the slope. Now the tangent of any function, the tangent line of any function is when is the line that hits that function at one point is the same as the instantaneous rate of change. So let's see, what do I want to do? I can think of a point on that graph, a comma f of a, and I can put a slider in there and see I can move this around. Let's make the slider go from negative pi over 2 to pi over 2. It's also, I just want to point out that there's these vertical asymptotes in this function. X equals negative pi over 2 and x is equal to pi over 2. And I could make them both dotted in the same color. And actually, that's all I care about now is what's in between those two dotted lines. So let's just stick there. And we can think of any point in this function in between those two dotted lines. And why do I care about that? Well, I don't know, because your math teacher tells you to care about that. What might I be interested in? I might be interested in the slope. The slope is a very important part of calculus. So what's the slope? Well, what we talked a lot about before was the slope between 2 points. So let's think of h. Let's think of this value h, where h is the distance between these 2 points, okay? And let's say if h can go between 0 and 2, then I can move, by sliding h around, I can move these 2 points from each other. They can be near or they can be close. And now I'm going to, you remember you have that formula, y2 minus y1 over x2 minus x1? Well, I'm going to call that the slope. So this is going to be f of a plus h minus f of a divided by h. And I'm going to put in that there's the point slope formula, y minus y1, which I could pick either of these 2 points as my y1 point. So let's pick the first point. Y minus f of a is equal to m times x minus x1, which is a. Boom. Okay, so now I have a secant line that goes through 2 points. And this is an average rate of change. Okay, so what h represents is the distance between these 2 points. So let's move a all the way back here. If I want to know the exact slope at that point, I might start by picking these 2 points, whatever these 2 points are, and measuring it. I might say I can get more accurate if I make that h smaller. So that whole idea of the limit as h goes to 0 is we're moving from an average rate of change to an instantaneous rate of change. Once h is equal to 0, I should have a tangent line, although in my formula the line disappears because then I would be dividing by 0, and I'm not allowed to do that. But that's the idea of h, right? That's how we move from average rate of change to instantaneous rate of change. I hope this doesn't bother you, but I'm going to just get rid of all this stuff because now we have something easier that's called the derivative. Okay, and if I wanted to, like Desmos is really good. If I just want to graph the derivative, this is the derivative of the tangent function right here. So, right, and then this thing is pronounced prime a lot of times. So if I think of a comma f prime of a, let's see if I move a around at any point. Now I have 2 points. This graph on top is the derivative. What is the derivative? Well, it's the slope. What is the slope? Well, it's the limit of that difference quotient. But that still may not mean that much to you. So I can write that thing that I had that was average rate of change. I could write this in another way, and I could say y minus f of a is equal to f prime of a times x minus a. Now again, I have this same thing that I had before, and I can slide it around with A. Where's my A slider? And now it's giving me the instantaneous rate of change. Okay, so it's the limit as h goes to 0, and that's what a tangent line is. Okay, that line is tangent because it touches the graph at only one point. And if I put this derivative function back up, and I put that point back on there, and now I think, how are those things related? This is complex. It's sophisticated. When you get this, you're on your way to getting calculus. But look, what's that point at right there? That point looks like it's 0, 1. Actually, 0, 1 is a point that we know is on tangent of x. Okay, sorry, 0, 0 is on tangent of x. The derivative should have, it looks like 0, 1. And what's that saying? It's saying that the slope of this tangent line to the curve is 1, and the value at the derivative is 1. So that's what's consistent between functions and their derivatives. And if you look at how this tangent line is changing, look at this. Is the slope steep or is it flat? Well, it's very steep. What's happening as I move from left to right? It's getting flatter. What's happening in the derivative? It's decreasing. Why is it decreasing? It's decreasing, it's going down because the slope is decreasing. Keep in mind that it's always positive. That's why it's always above the x-axis. So even though the slope is decreasing, it's still always staying above the x-axis because it's always positive. What happens at that point 0? Well, the slope stops getting flatter and it starts getting steeper. And what happens on the derivative? The derivative starts to increase. So what is the slope, the derivative? How are they all related? The difference quotient. The difference quotient and the derivative are the same thing. The derivative is the function, it's the slope function. So let's start and let's start with a new function because I talked a lot about the power rule, and I could say that we have, instead of like a trigonometric function, let's say we have a power function. Like let's say f of x is equal to, let's just say 3x squared. Okay, so what's the derivative function? What's the slope function going to be? Let's call it g of x, because Desmos, I could put in f prime of x and Desmos would do it for us. But now let's think of what is this going to actually be. It's going to be 2 times 3x raised to the 2 minus 1. Okay, so what I do is I take this 2 right here, I bring it down, and then I subtract 1 from the power. And what is an easier way of saying this? Well, this would be 6x to the first power, so 6x. And now, if you look at what's the slope of this at any point, let's say a comma f of a if I move this around, the slope there, right at 0, the slope of the tangent line is 0, and the value of the derivative is 0. If I move to the right, it's positive, and the derivative is above the x-axis. If I move to the left of that point, the slope of that function is negative, and it's below the x-axis. These are all things that'll take time to settle, but just this power rule idea. So what if I said f of x is equal to 4x to the third minus 2x squared plus x minus 7. you could think to yourself, and now it doesn't really matter what the graph looks like. What I'm trying to show you is how do you apply this power rule. G of x is going to equal, and this is the derivative. This is legal now that we use it. You don't have to do all that plus h business that just wastes your time, because you can bring the power down. This is going to be 3 times 4x to the 3 minus 1 minus 2 times 2x to the 2 minus 1 plus 1x to the 1 minus 1. Right, and you can do those. You can subtract 1 in your head by the time you get to this point in math class, but I'm just showing you how where you get it. So another way to write this would be, let's just start it from the beginning. G of x is equal to 12x squared minus 4x plus 1. And there is going to be an activity today where you're just given a function and you're asked to graph the derivative. And I think that's difficult, but I think what you should keep in mind is, like, let's say f of x, I don't know, let's say it's x cubed minus 2x. Okay, here's a good example of something that has a little bit of curvature. It's a third degree polynomial. That's why it has 2 humps. It's going to have, where you could think of, where is the derivative going to equal 0? Okay, and there's a relationship between a graph and its derivative, in that where a graph has a minimum or a maximum, its derivative has a slope of 0. So if I say f, let's do a comma f of a, add a slider for a. Let's see, we just want to go between -2 and 2. Where's my point? That looks good. Then I can do y minus f of a is equal to f prime of a times x minus a. You don't have to understand how all this stuff is happening, just that it can happen. And if I think of what's going on with that derivative, if I was going to graph the derivative, okay, this would be the process that I'm thinking. What is the derivative going to look like? Let's say we have these two points right here. Okay, we could define 3 regions. This is region 1. This is region 2. This is region 3. Okay, in region 1, to the left of that first hump, the derivative is positive. It's very steep, and then it's getting flat. And then when I get to that point, let's call it a like a very important point, because something's happening there. So maybe a critical. Let's call this a critical point right here. The critical point. When I get to that critical point, the slope goes from positive to 0. And then in my region 2, remember region 2 is going to be in between these next 2, well, we're calling them critical points now. So it's going to be in between this point and this point. What is the slope? It starts out as 0, then it gets negative, and it gets pretty steep. Maybe at -1 is the minimum, I'm guessing. And then it actually starts to get less steep. It's still negative, but it's getting less negative. Okay? And so there's this point where, like, the way that the line is moving changes is called an inflection point. That's a calculus thing. But now we get to the end of region 2, and we get another 0. That's another critical point. Then what happens after that, to the right of that point? It starts getting steeper, and then it gets steep and steep and steep. Is it positive or negative? It's positive. So how does that correlate to the graph if I do f prime of x? Well, let's look at it again. In this first region, let's say x is equal to negative 0.816. Okay, there's a lot going on this graph now. But in this first region, we said the slope is positive, and what's happening with the derivative? Well, the derivative is above the x-axis. At some point, the slope becomes 0, okay? And what's happening to the derivative? Well, that's where it has an x-intercept. And then it's negative, okay? What's happening on the derivative? Well, the derivative is below the x-axis. Why is it below the x-axis? It's below the x-axis because the slope of this is negative. And then what happens after you get to this second asymptote? Well, it becomes positive. And notice the asymptote lines up with the x-intercept here. And it becomes more positive, and it starts to increase. And I'm not sure if I answered every single question that was on here, but I think that's my best response to the derivative. Today there's something where you're trying to graph the derivative, which is difficult, and you're also looking at antiderivatives. So the antiderivatives, or I guess Riemann sums, is a whole nother topic. They're related, but I don't want to go into it because I feel like I've already kind of overwhelmed you with a lot of conceptual stuff. Hopefully this is helpful, and keep in mind you can always go back to watch this, or you can find other videos that are maybe better at explaining these things than me.